So, let us continue with the proof of this theorem which I stated before the first half of the lecture. So, we have given W is a subspace of V star and V star is finite dimensional. So, W is also finite dimensional. So, we can choose a basis of W. So, choose a basis. Remember W elements of W are linear form. So, I will call the basis to be F1 to Fr of W. Remember these are elements in V star. And by definition of W perp, then W not perp, W left circle, these are all those vectors in V which vanish on all linear forms in W. So, therefore, this is nothing but the intersection of H1 intersection HR, where HI is the hyperplane corresponding to this linear form Fi, that is HI is the kernel of Fi. I is from 1 to R. These are hyperplanes in V. Therefore, we have a codimension formula. Therefore, by codimension formula, codimension of codim left circle W in V is smaller or equal to the sum of the codimensions. I is from 1 to R, codim HI in V, but this is codimension of each one of them is 1 because HIs are hyperplanes. So, therefore, this number is R, which is dimension W. So, that was the statement. No, yeah, that was so R is the okay. So, I just want to show you the statement what we want to prove. So, we wanted to prove was dimension W equal to codimension this, and what we proved is codimension of left circle W is smaller or equal to codimension W. So, I have to prove the reverse inequality. So, to prove the reverse inequality, now what do I do? Let us choose a basis of W left circle. So, I will call it V S plus 1 to Vn in left circle W be a basis of left circle W. This is a subspace of V. So, I choose a basis and I number it like this. And I will, what will I do? There is only one way you can do. You can choose a basis and extend to a basis. So, I will extend this to a basis of V and extend it to a basis which I will not call it V1, Vs I have added, and this guy is S plus 1 to Vn of V. Then what we just proved above, every linear form which vanish on left circle W is a linear combination of the vectors V1 star, Va star. You see, all together for this, just note that V1 star, Va star up to Vn star, this is a basis of V star, and the later forms definitely they vanish on a basis of left circle W. So therefore, they will not contribute anything in the linear combination. So therefore, every linear form which vanish on left circle W is a linear combination of these vectors. This is a part of the dual basis V1 star, Vs star, Vs plus 1 star, Vn star corresponding to the basis V1 to Vn. Vs, Vs plus 1, Vn. This is the basis of W left circle, and therefore the stars will vanish obviously there, and any linear form which vanish on W star, therefore we will have only coefficients only from first S coordinate functions. So that will mean that W in particular the W has to be contained in the subspace spanned by V1 star plus K Va star. But that will mean the dimension of W cannot exceed more than S, because these are linearly independent. So W is a subspace here, and therefore W has to have dimension less than equal to dimension of this space which is S, and this S is nothing but codimension of left circle W in V. So these prove the other inclusion, reverse inequality. So actually therefore immediate consequence of this is the following, what we were looking for, that is, let me call it a corollary. So let W contain in dual subspace and we are assuming V and hence V star are finite dimensional. Then when you take left circle W, then that means you are coming back to a subspace of V, and then take the right circle, you get back W. Okay. And what is always true is this inclusion. This is always. This inclusion, this always holds. Without any finite dimensional assumption. So let us indicate the proof. Proof, as I said, W contained in left circle W, this is always without finite dimensional assumption. Therefore, I want to show the equality, I will show the other inclusion. So, to show left circle W and then right circle W is contained in W. Okay, but definitely I know if I take, but we know from the basic property that I listed above that if I take left circles, this, then they are equal. This we know as we have proved earlier. So, therefore, I know the codimensions. So, let us look at the codimension. Because of this equality, codim codim or dim, first let us take dim, dim of left circle W and then right circle W, this is equal to codim of there, because I want to apply, just let me show, I want to apply what just we proved, W equal to this codim, I want to apply this equality. So, this equal to codim 0 then 0 W this in, this is in V equal to codim, remove this. So, this is left circle W in V which is dim W. You see this guy in V, this guy is also in V. So, I am applying the earlier theorem to once to this and once to this. This is a subspace. So, I am applying one to this and one to this. So, that is, so I get codim of this equal to dim of this, no, dimension of this equal to dimension of this. But then see, one is a subspace of the other and their dimensions are equal, I showed. So, therefore, equality holds here, this implies equality here. That is what we wanted to prove. Okay, so let us, I want to note one very important example which is used by physicists. This is called also Lagrange multipliers. Okay. What is it? If you have, suppose you have n linear forms f1 to fn, be linear forms on a finite dimensional K vector space V. That is, they are elements of V star. And let us take W and let W be a subspace generated by these linear forms Kf1 plus Kfn. This is a subspace of V star, K subspace generated by f1 to fn. This one. Okay. Then Then by definition of this left circle W, this is nothing but the intersection of their kernels. Kernel F1 intersection kernel Fn. So which is also written sometimes as, this is the common solutions of these equations F1. Think of linear forms as equations. So this is F1 equal to F2 equal to Fn equal to 0. And this is a subspace of V, K subspace. Then therefore what is the codimension? This one is generated by n elements. So the codimension, codim left circle W in V is less equal to n. In particular, when are they linearly independent? F1 to Fn are linearly independent if and only if the equality holds above. That means codim of left circle W in V equal to n. Therefore, n linear forms in general define if they are linearly independent. If they are linearly independent, define what I should repeat. Define n codimensional subspace, namely left circle W. This is a subspace of V. Okay, and what we just proved above, that every linear form F that is in V star, which vanish on this left circle W, should therefore be a combination, is a linear combination of F1 to Fn. That is, every linear form F, we should be able to write this is lambda 1 F1 plus lambda n Fn, where lambda 1 to lambda n are scalars, and they are uniquely determined because we are assuming these F1 to F1 are linearly independent, uniquely determined. Since F1 to Fn are linearly independent. these coefficients lambda 1 to lambda n are called Lagrange multipliers. Of f because they are uniquely determined by f. So, therefore, I want to, so with this I want to state the following statement. So, theorem. Again I will assume V is finite dimensional. So, assume that V is finite dimensional. And W1, W2 are two subspaces of V star, K subspaces. As I said in the beginning last lecture that normally these correspondence work very well when you assume V is finite dimensional, because then V star is also finite dimensional. In case V is not finite dimensional, then V star becomes bigger than V, and therefore this correspondence will not have a good behavior. But if you restrict to finite dimensional subspaces, then it will still give some partial results. So, then W1 contained in W2 if and only if left circle W1 contains left circle W2. This is the analog. You see, the first theorem today I proved in the beginning was such a theorem for subspaces of V. But when you go to V star, that statement is no more true. So, we have to assume a finite dimensional. So, in particular, they are equal if and only if the left circles are equal. Okay, so let me also consider a double dual. So, let us go to the next page. So, now let us write it as an example. This is a bidual. Remember this process, from a vector space V, we have a new vector space V star. If V is finite dimensional, this is also finite dimensional. Then we can do the same process again, that is V star star, which I will denote by V double star. This is called bidual of V, which is a dual of the dual space V star. And there is a canonical map. There is a canonical homomorphism of vector spaces from V to V double star. There is no map from V to V star canonically, but V to V double star there is a Canonical map. What is the map? That map I am going to denote by sigma v, sigma suffix v. So what does it do? For a given vector x, I want a double dual. That means double dual means I want a linear form on v star. That means I want where this x should go to E, and E should be, no, not E, this x should go to somebody which maps v star to k. So what is that map? That means I need to know where do E go, arbitrary E go. So E and this x, you can do this E of x, evaluate E at x. So this is like evaluation map. It is called evaluation map. It evaluates a linear form on the given vector. Okay. So let us write down what is the kernel of this. So the kernel of sigma v is by definition all those vectors x in V such that it goes to 0. That means every linear form should vanish on x. So that means E of x should be 0 for every E in V star. But that is precisely the definition of V star left circle. Recall if W were a subspace of V star, W left circle was all those elements, all those vectors in V which vanish on the linear forms on W. So this is nothing but left circle of V star. But what is this? This is definitely 0, because given any vector space, we can always find given any x, if x were non-zero, we can always find a linear form which is non-zero on x by extending x to a basis and mapping x to 1 and everybody else to 0. So definitely this is 0. So therefore the first consequence is sigma v is injective, because its kernel is 0. Moreover, if V is finite dimensional, then V star is also finite dimensional and the dimensions are equal. Now once again applying that, V double star is also finite dimensional and the dimension is equal to dimension V star, which is also dimension V. So the linear map sigma V was from V to V double star, both have the same dimension, and this map was, we have checked, it is injective. Therefore by Pigeonhole principle, this is sigma V is bijective. So it gives an isomorphism between V and V double star. This is canonical isomorphism. If you remember, even if V to V star there is an isomorphism, but the isomorphism there is not canonical. Okay, this was the finite dimensional case. If V is not finite dimensional, then definitely sigma V is not surjective. This example I would write in, is given in exercises or supplements. Okay, we will stop here and continue for the next time. Thank you.